Okay, so we have a solar energy and storage practice final exam at the graduate level. So let's begin. Number one, the solar photosphere is approximated as a black body emitter of temperature given at 5,778 K. Part A, using Planck's law, show the spectral radiance B sub lambda of T for the black body radiation. So here we go here. Solar radiation as electromagnetic waves and photons, and I'm going to go through this rather quickly, skip some intermediate steps just to get through it. You have this as a reference for practice. So part A, Planck spectral radiance, you're given, we use this, B sub lambda of T is 2hc squared over lambda to the fifth times the quantity 1 over e to the hc over lambda k sub b t and then minus 1. This follows by counting photon modes in a cavity and multiplying the allowed mode density by the mean photon energy from Bose-Einstein statistics. Okay, part B, show Wien's displacement law from Planck's law and determine the wavelength of peak solar emission. So just going through this quickly, Wien's law, that's lambda sub max, T equals B. And then B is 2.898 times 10 to the negative third, K. So lambda sub max is 2.898 times 10 to the negative third over our K value, 5,778, which gives us approximately 5.02 times 10 to the negative seventh M, or NM, 502 NM. Okay, so here, letter C, calculate the photon flux density arriving at Earth near the peak wavelength, assuming the solar constant is 1,361, and 10% of the total irradiance lies within a 100 nm interval centered at the peak wavelength. Okay, so for letter C here, 10% of solar constant, I equals 0.10 of 1,361, so that gives us 136.1, our photon energy at 502. We use E equals hc over lambda. So E is going to be 6.626 times 10 to the negative 34 times 3.00 times 10 to the 8th over 5.02 times 10 to the negative 7th. E is approximately 3.96 times 10 to the negative 19th J. Our photon flux here, I over E, and it's going to be 136.1 divided by 3.96 times 10 to the negative 19th, which would give us about 3.4 times 10 to the 20 photons there per meter squared second. So here, moving forward, letter D, photovoltaic material has band gap E sub G equals 1.45 eV. Excuse me. Determine the cutoff wavelength for photon absorption and discuss the trade-off between thermalization losses and transmission losses. So here, E sub G equals hc over lambda sub C. Using lambda sub C of Nm, that's 1240 over Eg EV, E sub G EV. So lambda sub C is going to be 1240 divided by 1.45. And now from here, this is going to be lambda sub C is about 855 nm, and photons with a wavelength less than, or lambda less than 855 nm can be absorbed. Higher energy photons lose excess energy as heat. Lower energy photons pass through without absorption. Okay, so that's number one. Let's move along to number two. Again, I'm going to try to go through this quickly so you have just a reference to go back to. Okay, so number two. Okay, we have a solar power installation is located at latitude 40 degrees north. Okay, part A, derive the solar zenith angle as a function of hour angle, latitude, and solar declination. So this is a solar geometry and atmospheric effects problem. Solar zenith angle, it's going to be cosine theta sub z. That equals sine phi sine delta plus sine phi cosine delta cosine h, where phi is latitude, delta is solar declination, and h is hour angle. Okay, and that was more of demonstrating than deriving. Part B, At solar noon, I should have put show. Part B, at solar noon, so I'm sorry. Part B, determine the noon solar altitude angle on summer solstice, winter solstice equinox. So at solar noon, H equals 0, and theta sub z times the magnitude or absolute value of phi minus delta. Our altitude, alpha, is 90 minus theta sub z, and for our phi, that's equal to 40, so we just plug in here for summer solstice. Delta's plus 23.5 degrees, theta sub z 16.5 degrees, alpha is approximately 73.5 degrees. Winter solstice, negative 23.5 degrees, theta sub c is 63.5 degrees, alpha 26.5 degrees. Equinox, delta is 0, so theta sub z is 40, and alpha equals 50 degrees. Part C, using the mass approximation, AM is approximately 1 over cosine theta sub z. Estimate the air mass at sunrise when the sun is 5 degrees above the horizon. Okay, so sun altitude 5 degrees, so theta sub z is 85. So AM is approximately 1 over cosine 85. AM is about 11.5. Okay. D, discuss physically how Rayleigh scattering and aerosol scattering modify the solar spectrum incident on photovoltaic modules. So for letter D, Rayleigh scattering scales as 1 over lambda to the 4th. So blue and ultraviolet light scatter strongly. Aerosols scatter more broadly and reduce direct radiance, especially important for concentrating solar systems. Part E, explain why high altitude deserts are favorable locations for concentrated solar power systems. So high altitude deserts are favorable because they often have high direct normal irradiance, low humidity, fewer clouds, and less atmospheric absorption. Okay, so that takes care of number 2. Let's go on to number 3. Okay, so number 3, concentrated solar thermal plant operates between a receives temperature of 900 K and ambient temperature 300 K. I'm sorry, a concentrated solar thermal plant operates between a receiver temperature of 900 K and ambient temperature of 300 K. Sorry about that. Part A, calculate the Carnot efficiency. So the thermodynamics of solar energy conversion problem. So we have eta sub c equals 1 minus T sub c over T sub h. Eta sub c equals 1 minus 300 over 900, and we get about 0.667. So the Carnot limit is about 66.7%. Part B, assume the plant receives 500 MW of thermal input and operates at 65% of Carnot efficiency. Determine the electrical output power. Okay, so actual efficiency, okay, we take that eta equals 0.65 times 0.667, that percent, the Carnot limit in decimal form, and that's going to equal 0.433. And the power output here, we're going to take that 0.433 and multiply it by that 500. So we get the power output's about 217 MW. Okay, part C, the receiver behaves approximately as a gray body with emissivity equals 0.82. Determine the radiative power loss per square meter from the receiver surface. Okay, so we're going to use this formula given here, and we're just going to substitute our values. 900 to the 4th, that's going to equal, when we substitute everything in, just do the computation, 6.56 times 10 to the 11th, and what we're going to get is 30.5 kilowatts per meter squared. So net loss to surroundings would technically be this epsilon here this expression is T sub h to the fourth minus T sub c to the fourth is epsilon sigma times that quantity, which is only slightly smaller here. Okay, so, and letter D. In E are more conceptual textbook questions. D, discuss entropy generation mechanisms in real solar thermal systems. So entropy generation occurs from heat, transfer across finite temperature differences, frictional fluid losses, imperfect absorption, radiation losses, turbulence, non-ideal turbines, and parasitic pumping. Part E, explain why exergy analysis is often more useful than energy analysis for renewable energy systems. So part E here, energy is conserved, but exergy measures useful work potential. Solar energy has high exergy before conversion, but much of it is destroyed by thermalization, heat losses, and irreversibilities. Okay, so that's number 3. Let's move on to number 4. Okay, so number 4. Let's just get this in focus. Sorry. Sorry about the delay. Okay, 4. Consider a direct bandgap semiconductor with bandgap E sub g equals 1.12 eV. Part A, using the density of states for electrons in a semiconductor, derive the expression for intrinsic carrier concentration. So this is the quantum mechanics of solar cells type problem. So part A, intrinsic carrier concentration. We use this. N sub I equals square root of capital N sub E, capital N sub V, E to the negative capital E, G over 2 K sub B T. And N sub C is going to equal 2 times this quantity, 2 pi M star, M E star, M sub E star, K sub B T over H squared raised to the 3/2. M sub V is 2 times 2 pi M sub H star, K sub B T over H squared to the 3/2. So a major difference here is the subscript here, E and H, and N sub I is equal to the square root of capital N sub E, capital N sub V, E to the negative E G over 2 K sub B T. Very famous formula. Okay, so here, Fermi-Dirac distribution. Show how, for letter B, show how the Fermi-Dirac distribution determines carrier occupation probability. Also very famous. All this stuff is Fermi-Dirac distribution. F of E, that's 1 over E to the capital E minus capital E sub F over K sub BT, and then a plus 1. And it gives the probability that an electron state of energy E is occupied. Okay, letter C. Estimate the open circuit voltage of a solar cell at 300 K if the ratio of photocurrent to saturation current is 10 to the 10th. Okay, so here's solar cell equation at open circuit. We're given here I sub L minus I sub naught times this quantity E to the Q V sub OC over K sub BT and then minus 1. And this V sub OC equals K sub BT over Q. And that ln of I sub L over I sub I naught plus 1. And we're given that I sub L over I naught is 10 to the 10th. And at 300K, K sub BT over Q, that's going to be about 0.2585 V. So going over here, V sub OC equals 0.02585 ln times 10 to the 10th. And that's going to give you about, when we do the computation, V sub OC is about 0.595 V. Okay. Part E, discuss the role of excitons in organic photovoltaic materials. So here, letter E, in organic photovoltaics, excitons are bound electron-hole pairs. Because dielectric screening is weak, excitons must reach a donor-acceptor interface to separate into free charges. Okay, so that takes care of number 4. Moving along to number 5. Okay, so number 5. Oops. Okay, number 5. Silicon solar cell has the following parameters. Short circuit current I sub SC 8.5A, open circuit voltage, V sub OC of 0.68. V fill factor FF is 0.79. Incident solar power P sub IN 1000, and cell area 150 and centimeter squared. And then part A, determine the maximum output power. So this is a solar cell device physics and design type problem. So P sub max for letter A, determine the maximum output power. So P sub max for letter A, I sub SC, V sub OC, FF. So substitute. This would be 8.5 times 0.68 times 0.79. That gives you 4.56 W. Letter B, determine the conversion efficiency. So our area, we're going to change 100 for letter B. Change the area in terms of M, so 0.015 M squared for our area. Incident power, find is going to be P sub N equals 1000 times 0.015 gives you 15 W. Our efficiency is going to be 4.56 over 15, so convert that, that's a 30.4%. So this is very, very, very high for a silicon single cell, but mathematically follows from the given values, but very, very high. Okay, so not very feasible in that regard, but mathematically that would be the answer. Part C, if the series resistance increases, okay, explain quantitatively how the fill factor changes. So series resistance reduces voltage under load. V sub terminal is equal to V sub ideal minus R sub S. Higher R sub S lowers the maximum power rectangle, decreasing fill factors. Decreasing fill factor. Okay, and let's see. Letter D, I'm sorry. Just looking, I can't see. Sorry about that. Letter D. Discuss the Shockley-Queisser limit and derive the main physical assumptions behind it. Okay, so we're just going to talk about it. The Shockley-Queisser limit assumes one P/N junction, one electron hole pair per absorbed photon, no concentration unless specified. Radiative recombination dominates. The photons below E sub G are not absorbed and excess photon energy becomes heat. The limit arises from balancing absorption, emission, thermalization, and transmission losses. Explain the operating principles of PERC cells, tandem perovskite silicon cells, heterojunction solar cells. So PERC cells improve rear side passivation and reflection. Tandem perovskite silicon cells stack two absorbers with different band gaps to reduce thermalization and transmission losses. Heterojunction cells use crystalline silicon with amorphous silicon passivating / contact layers, reducing recombination. And that's for number 5. Moving on to number 6. Number 6 is a lot of textbooks / notes, canonical type stuff for the answers. Manufacturing reliability of solar modules. Part A for number 6, describe the major fabrication steps involved in manufacturing crystalline silicon photovoltaic modules. So, manufacturing and reliability of solar modules type problem. So letter A, typical crystalline silicon module manufacturing. This is the steps, typically in this order: silicon purification, ingot growth, wafer slicing, surface texturing, dopant diffusion or junction formation to passivation, to anti-reflection coating, to metallization, to cell testing, to strigging and tabbing, to encapsulation, to lamination, to framing and electrical testing. Okay, so this is more textbook type stuff, direct, very direct. Explain the role of anti-reflect, for letter B, explain the role of anti-reflection coating, surface texturing, passivation, layers. Layer B, anti-reflection coatings reduce Fresnel reflection. Surface texturing traps light by increasing internal path length. Passivation reduces surface recombination by lowering defect state density. Part C, a module undergoes thermal cycling between negative 20 degrees Celsius and 85 degrees Celsius. Discuss the dominant mechanical failure modes. Okay, so part C here, thermal cycling causes solder fatigue, ribbon cracking, encapsulant stress, delamination glass stress, and micro cracks in silicon wafers. Part D, explain the physical origin of potential induced degradation, PID. Potential induced degradation occurs when large voltage differences drive ion migration, especially sodium ions, causing leakage currents and shunting. Part E, discuss the trade-offs between efficiency, cost, scalability, environmental impact for monocrystalline silicon, CDTE, CIGS, perovskite solar technologies. So, for letter E, monocrystalline silicon, high efficiency and mature manufacturing, but energy-intensive purification. CDTE, low cost and good thin film performance, but cadmium toxicity and tellurium scarcity matter. CIGS, high thin film efficiency, but indium and gallium supply are concerns. Perovskites, high efficiency potential and low temperature processing, but stability, lead management, and scaling remain challenges. So that's number 6. Moving along to number 7. Okay, so 7. Also a bit straightforward textbook stuff. A lithium ion battery operates at normal voltage 3.7 V and capacity 5.0 Ah. Calculate letter A, calculate the stored energy in watts, hours, and joules. Okay, so this is a lithium ion batteries and electrochemistry type problem. So this for letter A equals VQ equals 3.7 times 5.0, that's 18.5 WH. Converting to joules, we take that, multiply by 3600, we get 66,600 J. So we wind up with E equals 18.5 WH. And for 6.66 times 10 to the 4th J. Letter B, the battery has internal resistance 0.045 ohms. Determine the resistive heating during a 4A discharge. So letter B here, P equals I squared R. P equals 4 squared times 0.045. 0.045 P is 0.72 W. C, derive the Nernst equation for electrochemical cells. Okay, the Nernst equation, E equals E degrees minus RT over NF ln This is just going to talk about it very briefly, not go into the whole thing. It comes from delta G is equal to delta of G degrees plus RT ln Q, and delta G equals negative NFE. Letter D, explain lithium intercalation in graphite anodes from a quantum and solid state perspective. This is textbook type answer. Notes type answer, canonical. In graphite, lithium ions intercalate between graphene layers. Electrons enter graphite conduction states, while lithium ions occupy stable sites between carbon planes. Process depends on band structure, chemical potential, and diffusion through layered solids. Letter E, discuss thermal runaway. Letter E, discuss thermal runaway mechanisms in lithium ion batteries. So here, letter E, thermal runaway occurs when heat generation exceeds heat removal, SEI breakdown, electrolyte decomposition, separator melting, internal shorts, and cathode oxygen release can create accelerating exothermic reactions. Letter F, compare lithium ion technology with sodium ion batteries, solid state batteries, flow batteries, hydrogen energy storage. So for letter F, sodium ion, cheaper materials, lower energy density, solid state, potentially safer and higher energy density, but interface and manufacturing challenges. Flow batteries, scalable energy capacity, useful for grids, lower energy density. Hydrogen, long duration storage, but low round trip efficiency. And that's all for number 7. Let's move on to number 8. Okay, so number 8, solar farm produces power according to function P of t equals P naught sine squared of pi over t over 12 for 0 is less than or equal to t is less than or equal to 12 hours with P naught equals 150 MW. Part A, determine the total daily energy production. So this is a grid storage and renewable integration. So we use this integral for A equals this from 0 to 12 P naught sine squared of pi t over 12 dt. Luckily, the average value of sine squared over a half cycle is just 1/2. So in this situation, E is P naught times 12 times 1/2. E equals 150 times 6 equals 900 MWH. Part B, a battery storage system must provide constant output power of 60 MW over a 24-hour cycle. Determine the minimum storage capacity required. Okay, so for B, demand over 24 hours, ED equals 60 times 24, that's 1440 MWH. Solar only produces 900 MWH, so the solar farm cannot supply constant 60 MW 24 hours without extra generation. Minimum daily deficit, we get 1440 minus 900, that's 540 MWH. So no finite battery solves the problem over repeated days. The plant needs more solar generation or lower demand. Okay. Letter C, estimate the round-trip efficiency losses if the storage system operates at 88% efficiency. So if 900 MWH enters storage, use cycle with 88% efficiency, E sub usable equals 0.88 times 9,000 equals 792 MWH. So loss is 900 minus 792, 108 MWH. Letter D, discuss frequency regulation and inertia challenges associated with high solar penetration. Okay, letter D, high solar penetration, that reduces rotating machine inertia. Frequency can change faster after disturbances, requiring inverter-based fast frequency response and storage. Letter E, explain the role of smart inverters in modern renewable and energy grids. Letter E here, smart inverters provide voltage regulation, reactive power support, ride-through capability, and frequency response and grid forming, grid following control. Okay, so that takes care of number 8. Let's move along to number 9. A lot of that is very much like standard. Okay. Number 9, a building wall consists of exterior glass layer, air gap, and thermal storage wall. Part A, using radiative and conductive heat transfer principles, derive the equilibrium temperature equation for the wall. We'll go through this quickly. Solar architecture and building physics. So at equilibrium, Q sub absorbed equals Q sub CONV plus Q sub rad plus Q sub COND. This is CONV and this is COND. A possible wall balance is alpha I equals H times quantity T sub, the wall temperature minus T sub A plus here epsilon sigma times the quantity T sub wall temperature to the fourth, T sub surrounding to the fourth plus K over L times the quantity T sub wall minus T sub I. Okay, and now here, let's see here for this is where T sub, sorry, I wrote that T sub, that W, that's the wall temperature. Okay, and this is SUR there, if it's legible. Hopefully this is legible. Okay, part B, explain the operating principle of a trum wall. Okay, a trum wall absorbs solar radiation behind glazing, stores heat thermally, and releases it into the building with a time delay. Okay, part C, discuss how emissivity selective coatings improve building thermal performance. So C, selective coatings can absorb solar radiation strongly while emitting weakly in the infrared, reducing nighttime thermal loss. Part D, a building roof receives average irradiance 750 over an area of 120. If photovoltaic efficiency is 24%, determine daily electrical production, assuming 7 equivalent peak sun hours. So our power output here is going to be 750 times 120. That's going to give us 90,000 watts, 90,000 W. PV output, P sub ELEC equals 0.24 times 90,000. So we get 21,600 W, which is 21.6 kW. So our daily energy, multiplying that by 7, it's going to be 151 times 2 kWh per day. Letter E, we're going to briefly discuss passive cooling methods that reduce solar thermal loading in urban environments. Okay, so passive cooling methods include shading, high albedo roofs, radiative cooling surfaces, ventilation, thermal mass, green roofs, and urban tree cover. Okay, so that was brief, that one, number 9, and this is number 10. Okay, so number 10 is more canonical again. Topics in solar energy and storage. Discuss the detailed balance approach to for letter A, discuss the detailed balance approach to photovoltaic efficiency. So A, detailed balance equates photon absorption and emission. In a solar cell, current arises from the difference between absorbed solar photons and emitted recombination photons. Letter B, explain the physical significance of quasi-Fermi levels in illuminated semiconductors. So in illumination, electrons and holes are not described by one equilibrium, Fermi level. Instead, they have quasi-Fermi, E sub Fn and E sub Fp. Their separation determines the voltage. So QV is approximately E sub Fn minus E sub Fp. Okay, so C, describe hot carrier solar cells and why they could exceed the Shockley quasar limit. So here, hot carrier solar cells attempt to extract carriers before they thermalize to the lattice. If successful, they reduce thermalization losses and can exceed single junction limit. Letter D, discuss artificial photosynthesis and photocatalytic hydrogen production. Artificial photosynthesis uses light absorption, charge separating, and catalytic reactions to produce fuels such as hydrogen. A key reaction is water splitting here. Okay, so in letter E, evaluate the major physics and engineering challenges associated with achieving a fully renewable electrical grid dominated by social energy. Well, you could write quite a lot about this. This is a condensed version. Challenges for a solar-dominated grid include intermittency, seasonal mismatch, storage duration, transmission expansion, inverter stability, material supply, land use, recycling, and maintaining reliability during low sun periods. And that's all for number 10, and we'll move on to number 11. Okay, number 11, discuss a hybrid renewable energy system for a remote research station with the following requirements: continuous power demand, 250 kW, average solar irradiance, 5.5 kWh per m squared per day. Autonomy requirements, 7 days without light. Includes solar array sizing, battery storage sizing, thermal management considerations, inverter efficiency assumptions, seasonal variability, analysis, reliability, and redundancy considerations, economic trade-offs, and environmental and materials constraints. So this continuous demand is 250 kW. So our daily energy demand, E sub D, is 250 times 24 is 6,000 kWh per day. With inverter efficiency, this eta sub I equals 0.94, and then E sub PV is 6,000 over 0.94. This is going to give you 6383 kWh per day. Okay, now from here, solar resources, 5.5 kWh per meter squared per day. Assume that PV bottle efficiency 22%. So E per area equals 5.5 times 0.22 equals 1.21 kWh per m squared per day. Required area is 6383 over 1.21, so that would be 5,275 meters squared. And with a 25% design margin, area is about 6,600 meters squared. Battery autonomy for 7 days. Okay, that's E sub BAT equals 7 times 6,000, 42,000 kWh. for 80% usable depth of discharge. E subrated 42,000 divided by 0.80, that's 52,500 kWh, 52.5 MWH. With round trip efficiency and aging margin, a practical design may require roughly 60 to 70 MWH, 60 to 70 MWH. And thermal management must remove battery heat, prevent freezing, and avoid high temperature degradation. A robust design should include redundant inverters, spare strings, fault isolation, fine suppression, monitoring, and possibly backup long duration storage such as hydrogen or diesel only for emergency reliability. So this was just a practice exam, extra practice problems. And thank you for watching, and have a great day.